So let's see. Hopefully they can see this. Okay, so the three main terms. I want to go over each of those again that we're dealing with most of the measurements. They are voltage, current, which is abbreviated I, of course, and resistance. Voltage is a potential difference. So we talked a little bit about that potential, kind of potential energy for the charges. So we've got that definition. We call it potential difference. It's really a potential energy difference between 2 points. And depending on charge, so per unit charge. But in sort of layman's terms, the way you can think about this is it's sort of electron pressure. It's how hard are electrons being pushed. Higher the voltage, the more force putting them through. Essentially, though, it's how much energy are they converting from their electrical or stored form into something else, light and heat, or mechanical energy in a motor, something like that. Current, is, as we said yesterday, is the amount of charge passing a point per second. Essentially what this is a count of how many electrons are going through. So the flow rate. When we're measuring voltage, we're always measuring across something. Normally, I mean, we could measure wires, but very little energy is lost in the wires of our setup. It is measurable, but not very much. So we usually don't measure across a wire. We measure on the two sides of, say, a resistor. Mm-hmm.
So the voltage, if the electrons are pushing harder, like if there's more voltage,
yep,
then wouldn't that mean that the current is going to be bigger?
Very possibly. And we're actually, Ohm's law is the relationship among these three things. So by the time we're done, we'll see exactly how those three are related. Yeah? Amps, yep. So let's get that. And 1 amp, or ampere, the full name, abbreviated A, is equal to 1 coulomb of charge per second. I don't know how they came to the number of electrons that is a coulomb. It's just a number. Yep?
So voltage is measured in volts. What is that?
A volt, in green, 1 volt is equal to 1 joule per coulomb. So it's a joule for a whole bunch of electrons. Or per a whole bunch. Resistance doesn't really have that nice relationship. Resistance is the, what's the right word for this without using resistance? It's basically how difficult is it to push electrons through. I'm struggling to find the right word for this, but I'll put that sort of layman's term down here. How hard is it to push electrons through it, a substance or an object? Oops. The resistance, the
How about refusal?
it's not a refusal though either, because nothing is so resistive that electrons can't
The attempt.
not attempt.
Conductivity.
It's related to that.
The friction.
It's sort of a friction because it's
The
dealing
ability to
with
not be affected by it.
what's that?
The ability.
That's not a very that's not a good one.
What about impeding or slowing?
Impeding is good. Impedance is another word that's used a lot in electronics for something very much like resistance.
Tyler, look it up with Siri.
That's what I just did.
Oh.
The Kirchhoff index KF also
What about
signifies
reduces,
resistance
something
and-
that reduces the...
No, I don't like reduces either. This is going to be fun to watch. Hindrance is pretty good.
Hinders the speed.
Resistance is an electrical quantity that limits how the device or material reduces an electric current.
Still don't like that reduces.
What?
Wasn't it kind of like a capillary versus
No,
a...
you never know, Justin.
A material's opposition to the...
Opposition is the word I was looking for. There you go. The opposition.
Didn't we already have opposition?
What is that?
We could have just looked in our notes.
This is physics.
Yeah, we got to. Well, I want the right meaning of the word because it is reducing it, but opposition is the correct word. We measure it in ohms. And we abbreviate it with omega because O would look like a 0. Mm-hmm.
This is off topic, but what is the lowercase omega symbol?
Kind of like a W with a curly.
Oh yeah.
It doesn't kind of match. It's not like a butt.
It's got
like I drew it, but-
We use that for something.
Yeah, it's.
Yeah.
You use it in physics or maybe in math for frequency.
Isn't it
That's better.
calculus?
What's that?
Isn't it calculus sometimes?
Yeah, I'm sure it is. I don't remember exactly how they'd use it. We use it as angular velocity. So we actually saw it. You might remember this.
Yeah.
Yeah, that's the formula I hated.
Oh yeah.
Rotational kinetic energy.
That's the one.
So it's used as an angular velocity in physics.
I thought we replaced that with like a scene.
We did, but this is what it starts out. This is the more general form of spinning something. We were only doing rolling.
Go back to our time.
Okay, yes, Matt.
Is there things that an ohm stands for? Like,
Not in the same way. By the time we get done with this lab and have Ohm's law, which will be the end of the hour, we can look and see the relationship, but I don't want to give it to you right now. There is not the nice, easy definition. It's really how are the current and voltage related, is what this is. And that's why we call it Ohm's law, because Georg Ohm was the first person to show how those were related. Much more difficult measurements than we can now make with our handy-dandy digital multimeters. He had to design his own tools that he could then read to do those. Interestingly, though, would you reach up into the first cabinet and get me some of
Hi, Ryan.
on the bottom,
You didn't know he was
some of the
there?
dial
No.
machines?
Ryan.
Yeah, that one. That will work. So this is an example of a much older.
Oh jeez.
This one's a current measurement. They didn't, so they used to come in just one flavor, so you could measure current or voltage, potentially resistance, but you need a power supply to do that inside. And so the needle type, but even these
It's like a
doesn't look.
The Geiger counter's up there, it's a yellow thing.
guide.
same.
Well, you never need a Geiger counter unless Fallout.
So what is that for?
You got one on your Bitcoin.
Oh, yeah. I can
It's got a dial and it's got a needle.
And
Yes, so it is similar in that regard.
that's about it.
Well, what else are you looking
So these, though, are more of a mechanical way that would have to be that you pass current through a little wire that deflects this in its own little magnetic field, and so it would have to be calibrated. And this is sort of the way that it was first started. Well, I'm sorry I'm boring you, Ryan. Whatever.
Sure.
Okay.
There right now, thing.
So what I want you to do and we went through the circuit diagram. We'll practice lots with circuit diagrams, so you don't need to master that at this point. Let's go back, though, and finish up. I'll put out the materials. Finish up the measurements if you haven't, and then work on the graph if you haven't gotten that.
I did the graphs by myself, actually.
Then